That's what it's going to do. So I can apply sigma to that number. Let's say this is E1. Okay, sigma of E1 might go, well, if maybe 1 goes to 3, then I'm going to get an E3 there. But let's write this down. All right, so let's just look for clarity. Let's apply the transpose, this is transposition 2, 3, so it just switches the numbers 2 and 3. And if I apply that to ijk, let's do, you can think of this as being ijk. I want to do the E1 because it's clear. E1, 2, 3. Okay. It's going to be E1, E3, E2. That's it. So this is what the action does. This says switch the basis elements. So that means that if I had, let's take V to be 3 E1 plus 6 E2 minus 2 E3. Random numbers. I don't know where they came from. Okay. Then what is 2, 3 acting on V?
Change the, what's it, so it's going to be 3E1
Yeah.
plus 6E3 minus,
Yep.
minus 2E2, yeah.
Switches the 2 and the 3.
Okay.
That's what that does. So this is an example, all right?
The faucets just got in the way.
The faucets.
Yeah.
This is,
But you said it out loud, so.
okay. So a geometrical picture, let's think about our bases. They're orthonormal, so I can write them like this. Okay, E1, E2, and E3. After the action, I get a new set of bases. This says switch 2 and 3, so 2 and 3 acting on that basis gives me E1 stays the same, but now I've got E3 down here and E2 right here. Notice what this did to the handedness of my coordinate system. I started out with a what handedness?
You started out with right-hand system, and now you've got a left-hand system.
So called right hand, left hand. It turns out that odd elements, so if the sign of this group element in the symmetric group is odd, and it has odd parity, what changes the parity of space-time? This is called a parity transformation. Physicists use this all the time. Okay, so this is a back-ended way of doing it. Physicists do it in a kind of weird way. They invert all the axes by taking x to minus x. Well, this is another way to do it, and I think it's easier to really apply. So this is a parity transformation. Another thing that you can use the symmetric group action for is if you have a wave function. Okay, and this is a multi-particle wave function. So I have psi, let's call it psi 1 of x, and I'm going to use the big boy notation, psi 2 of x, and so I have a system of n particles. With the corresponding wave function psi 1 to psi n. Okay, and you have to look at the tensor product of the Hilbert spaces, and this is a tensor. And you might have a better understanding of what this is in a few weeks. But right now, just think of it as if you took a Cartesian product, so that these are different coordinates, if you just listed things out side by side, okay, as a list. All right, so if I do the same deal where I start switching the numbers around on my indices here, that has the effect of switching particles around, right?
Okay.
So if I switch 1 and 2, then I get psi 2 tensor psi 1. Okay, what this does, this is you've heard of indistinguishable particles?
Mm-hmm.
Okay, if you start switching the order of the particles, you're able to determine the statistics. So fermions, let's look at fermions are guys with spin 1/2, and it turns out that they obey Fermi statistics. I think it's Einstein with Fermi statistics. Is that the big word? I forgot. It's been a year or two since thermo. So you've got fermions and bosons, and fermions obey. They get a negative sign when you switch the order. So psi. Let's do 1, 2 of psi 1 tensor psi 2. That's going to be minus psi 2 psi 1. If I do a parity transformation, or it's not a parity transformation here, but if I switch the order of the particles, I get a negative sign. And that's really important. That changes everything for fermions. That's why the atoms don't collapse. That's what gives us, because bosons can be in the same place at the same time, fermions can't. And it comes from this relation here. Okay, so if I do the same if I do the same action on bosons, it doesn't hurt anything. Okay. They have a symmetric, they're symmetric under interchange of particles, and fermions are anti-symmetric under interchange of the particles. Okay, so this action is not the correct action, right? You would need to include, for fermions, you would need to include something like the sign of sigma. The sign would go out in front of your, whatever your map was. All right, so this is some stuff to, group actions are super important. They really are at the heart of physics. Let's talk about the action of the Lorentz group on Minkowski space.
Wait, can I back you up for a second? This thing about fermions and bosons again. Let me see if I understand that.
Okay.
All right, you said that fermions are spin 1/2 particles.
Mm-hmm.
Okay, so 1/2 spin particle means that you would have to, something about
So
two transformations puts it back to where it was. Is that where this comes from?
we can, let's see, when we talk about tensor products, no, actually when we talk about matrix exponentials, I'll show you
Okay.
exactly the mathematics behind what
Okay.
you're talking about. This is slightly different.
Okay.
This is coming from the statistics element. In regular old quantum mechanics course, in an undergraduate course, for example, these are taught as two separate things. They tell you, fact one, fermions have half integral spin, and bosons have integral spin. And then they keep going with that. That's just a name. And then later on they say, oh, by the way, fact two, this is an experimental, empirical fact. When we study fermions, they have the effect of switching the sign of the wave function when we switch particles. They're anti-symmetric. And bosons. So they introduced that as an empirical fact. If you go to quantum field theory, this is proven. This is a result of the quantum field theory, which is another sort of triumph of quantum field theory. That's why it's so powerful. Because now this thing which we empirically observed is now just wrapped into the theory.
Cool.
Okay, so let's see. talk about